Is unitary quantum mechanics consistent with Born probability?
So you've all heard in a series of previous talks reference to the fact that the time development in quantum mechanics is unitary, and then everybody mentions at some point that it gives probabilities for most outcomes, and that the probabilities are described by the Born rule, that is, that goes the measure of the quantum state corresponding to some outcome, or in some simple cases as psi squared. So what I want to do here is, first of all, warn you, absolutely nothing I'm going to say here is original. And what I want to talk about is two things. First is to show that the excuses that are often given for saying that the Born probability is provably the right probability to use with unitary quantum mechanics all have hidden or sometimes explicit anthropic arguments behind them, and that in fact unitary quantum mechanics really looks on the surface to be quite inconsistent with the Born probability, or with any probability that would make any sense to us. And then the second half will be an advertisement for Jacques Mallah's many computations interpretation of quantum mechanics, in which he gives an explicit argument for why Born probabilities could arise naturally, not that they must, not that they're provably required, but that they could arise conditionally dependent on what the quantum state is. So that's the outline of where I'm going. I think most people know this, but Jamie said, give an introduction for the non-quantum people. A quantum state is a vector in a Hilbert space. Its time evolution is given by a unitary operator, like a generalization of the Schrödinger equation. The local description of what's going on is not given in general by a pure state, but by a trace over the environment with which the local state is entangled, and that's described by a density matrix. And if that's the whole story, there's no little Bohmian dot or alleged collapse process or anything like that, then all the possible outcomes that are allowed by that unitary development in some sense occur, but they turn into decoherent pieces which no longer exhibit any quantum interference effects, at least as measured by any sort of more or less local measurement. And those distinct pieces are called many worlds. And this is the pure unitary development is usually described as the many worlds interpretation of quantum mechanics. Now, the point is the unitary development itself has no probability in it at all. It's completely deterministic. So the question is, where does the probability come from? And once you've made an excuse for having some probability, why is that probability proportional to the quantum measure, the psi squared rule, the Born rule? So let's look first at a toy case, the toy case that everybody starts with when they start thinking about, well, what should we see with many worlds? Everett started with this and so on. Let's look at the Schrödinger cat experiment, where, say, it is driven by a quantum measurement of a spin. And if the spin is measured to be up along some chosen axis, then the cat is allowed to live. If the spin is measured to be down, then the cat is killed. And this experiment can be repeated on a large number of cats. I'm not recommending that anybody do that, but in principle, Gedanken experiment can be done. We could, for example, start with the initial spin lined up. We'll try and be a little bit nice, make it lined up a little more with the up axis than with the down axis. The sum of the squares adds up to 1. So could be a probability 1 squared. And we start with a cat in some sort of environment, which consists of everything around, everything that might interact by any field with the cat. And since cats have gravity, it's everything. And then the measurement process just consists of what we've heard called an instrument. It's some sort of process by which the interaction, just ordinary quantum process, where the interaction of the cat with the environment leads to a change in the environment, change in the cat and the environment. The spin up gives the live cat with an environment that might include you and certainly everything that interacts gravitationally that sees the live cat, plus there's a component with a spin down, a dead cat, and an environment that sees a dead cat. And here's the part where everybody gets surprised when they first think about it and either gives up on many worlds or finds some excuse to sort of talk their way over it. Each of these results is perfectly experienceable. You don't tell yourself, oh, I'm not fully experiencing this because my coefficient is 0.6. So each of these is a perfectly good world. And you do this experiment on a large number of cats, you end up with many different worlds. They're all distinguishable because they all have different live cats in them. And as you let n, the number of times you've done this type of experiment, get to be big, you can just count worlds. And of course, it's a binomial expression. Almost all the worlds have about 50% of the cats live. But we've set this up so that we know that's not the actual result of real experiments. We've set it up so that 64% of the time the cat lives. And after you've done many, many experiments, just ordinary classical statistics sets in, and you will find most of the time you're over here with about 64% live, not at 50%. So you don't get the probabilities in the obvious way by just counting how many worlds look one way and how many worlds look another way. Somehow or other, the quantum measure has snuck in a way that is surprising. So let me just say a little bit about what those worlds are, because there's a certain fuzziness about the definition of worlds. And I just point you to the standard explanation of it, which is Wojciech Zurek's so-called Ein selection, environmentally induced selection, where certain types of states of the local system give sort of stable elements of the density matrix in the sense that they don't really care, at least for moderate lengths of time, what's going on in the outside world with which your local system is entangled. So for example, if you have a live cat, or could be a dead cat, and its density matrix is represented this way in a live cat, dead cat basis, then for a little while, it's going to continue to look the same. This density matrix will be reasonably stable. If, on the other hand, you'd sort of perversely pick as your basis states live cat plus dead cat over root 2, and live cat minus dead cat over root 2, which from the point of view of Hilbert space are just fine states. There's nothing wrong with them as local states. All hell breaks loose when you look at the density matrix over time. You get these off-diagonal terms that are fluctuating all over the place, depending on things that are going on remotely and with things that you're entangled with that you have no control over and can't really detect. So these so-called pointer states, the one that corresponds to the type of macroscopically coherent outcomes that we are used to thinking about and experiencing, those are selected not by the structure of Hilbert space, but by the structure of this interaction with the environment. So let's see. What happens as time goes forward? Let's say you start off with a pure state expressed in some funny basis where there's a whole bunch of off-diagonal terms in writing the density matrix for that state, because you picked just sort of a random basis. What happens as time goes forward? Well, the increasing entanglement with the outside world causes the off-diagonal terms that connect versions of the outcome that are macroscopically distinct to essentially vanish. And as time goes forward, then you get off-diagonal terms only between things that are macroscopically closer and closer to each other. So that's the basic standard picture of what's going on with decoherence and the emergence of classical reality from the quantum underlying picture. So definitely not saying anything new here. Now, what happens when you have two really distinct states, macro-distinct, the live state and the dead state? And there are essentially no off-diagonal terms between them. You're not, in other words, you're not going to get any quantum interference terms between these macroscopically distinct states. We set it up so that this guy had a coefficient of 0.8 and that one had a coefficient of 0.6. In other words, 64% probability here, 36% probability there. But why? The internal structure of this density matrix, it's not in any systematic way different from the internal structure of that density matrix. Whatever your rule is for counting how many experiences there are, other than for the cat, of course, within this, that are represented by this piece of the density matrix and that are represented by that piece of the density matrix, there's no systematic reason for there to be more here than there. So there's nothing about what I've said so far that would break that initial toy argument that says we should end up with equal number of live cats and dead cats, regardless of the exact orientation of the initial spin that went into that measurement, which would make those coefficients different from 0.6 or 0.8. So we still haven't accounted for how it is that the Born probabilities can arise in any natural way from this purely unitary time evolution of a quantum state in an environment. Let's look at a little bit at the sort of problems that would come up if we just try and count worlds. The live cat might have quantum fleas, and within their brains, little fleas have small brains, so their small quantum events are causing them to decide to jump or not to jump. But those are macroscopically distinct states. So the live cat is turning into a whole bunch of macroscopically distinct cats, depending on the quantum branching of each of those fleas jumping. And that, if we just tried counting worlds, that would lead to something very strange. Because say the experiment's done on Tuesday and it's 64%, or there's one live cat world, there's one dead cat world. Now the quantum fleas start jumping and there become many, many live cat worlds. There's still only one dead cat world. So the probability of an event would not be determined just after the event. It would keep changing in the future, depending on how much quantum branching happened in each of those outcomes. And there's no reason whatsoever for that quantum branching in the different outcomes to be matched up in the same way. So one problem with this toy model has been pointed out by David Wallace. He said, look, this branching is going on all the time, so you can't really pick a bunch of little regions on the diagonal of the density matrix and treat them as clearly separate from each other and count them up, because the regions always have a fuzzy edge. They're always in the process of splitting. They've got some off-diagonal terms connecting them, but those are getting smaller, and then you wait a little longer, now smaller regions are still connected. So what are you going to count? It's not like a clear, distinct count. So that's a fair point. And then he goes from that, so he says, well, you can't count, so all bets are off. We get to invent any rule we want. If you have a collapse process, outside the unitary development. Yes, you get to invent any rule for that collapse process. But here we're saying, what if we don't? What if we just have the unitary time development? And Wallace's argument, which I like to cite because it makes explicit what's implicit in the more formal sounding arguments, namely the strong anthropic element of the argument, says we're rational agents. We have to decide what to do. And there's some phrase, philosophical phrase I don't understand, called diachronic consistency. Basically, it's supposed to mean we're supposed to be able to make decisions, and they're supposed to be reasonably self-consistent and not jumping around all the time, where we should have made the other decision if only we'd known that the quantum cat was going to have quantum fleas. So he says, if you want to have diachronic consistency, then you need the Born rule. And the argument is basically that if quantum probability of an event is determined once the event's over, and then future branching, which can be called context if you want, does nothing to do, has no effect on the net probability of that outcome, then as Gleason showed, the only sort of quantity that can represent the probability and obey that rule is the quantum measure. You can think of it as sort of a conserved fluid flowing, and the amount of that fluid gives you the probability. Problem is, as we saw, if we just start with the unitary time development, there's no reason for that rule to be true. And to his credit, Wallace gives sort of an argument where a skeptic says, this doesn't make any sense. It has nothing to do with the theory you're talking about. And the answer is just, it better make sense, because otherwise the world will have a completely incomprehensible probability. So he says, we have to have that this future branching has no effect on the probability of past experiments or events, because otherwise it just gets crazy. But and in one way or another, the same argument gets used less explicitly anthropically in all the past arguments. Gleason says there's non-contextuality, independent of splitting into parallel worlds. Zurich himself used additivity, where he says, well, we can do a symmetry argument about a whole bunch of sub-outcomes of experiments that weren't done, where you divide up every outcome into a bunch of little pieces with equal measure. But we don't do that experiment, and it's unclear why that should have anything to do with the probability we see. And every week or so, there's another argument that comes out. It always comes down to the same thing. If it wasn't the Born rule, then it would be crazy and we couldn't make sense of the world. But we have what's supposed to be a complete theory, and we're not supposed to be able to tell it what result it's going to give us. It's supposed to tell us what the result is, and then we can check whether that result agrees with our experience. Patrick Van Esch has written this up nicely, describing the implicit anthropic arguments in all these past alleged proofs. And he gives a nice analogy. He says, what if you, as happened historically, are trying to derive Euclid's fifth postulate from the first four, and you're just sure it can be done, but finally you say, no, actually it can't be done. You can make a consistent geometry, either with the projective postulate or with Euclid's postulate, and there is a way of proving it. My favorite example is more from physics. Think of black body radiation. If you say black body radiation is finite, you can easily derive from classical thermodynamics that the intensity has to go as temperature to the fourth power, if you assume it's finite. And so many people say, well, it must be finite, otherwise things are crazy. But classical equipartition says it ain't finite. It says that things are crazy. And insisting that, well, we can make the argument about how the world would be if it wasn't crazy is a good way to not discover quantum mechanics, to not be Planck and not find that we need a way around classical equipartition. And the way around it is that the classical physics is false. So let's go to what is counted. Now I'm getting into Jacques Mallah's ideas. He says, look, all you can count is observation. If you can't see it, you can't count it. And there's another key point. We don't really need the absolute counts, which Wallace has shown don't really exist. All we need is ratios of counts to get probabilities. If we know the ratios of the counts of different outcomes, we can say what the ratios of probabilities are, and we just normalize, we got all the probabilities. So we're interested in what constitutes an observation. And here Mallah says something, that really should be kind of obvious. Assume that, the assumption being that we are in fact part of the physical world, that we are not some sort of external agent that can intervene in the world in some way that doesn't obey the unitary time evolution. So he says an observation is really a computation performed by some subsystem of the overall system. And in order to count as a computation, to be this sort of thing that we call a thought, you have to have some ingredients, like there has to be some memory, you have to have some ability to predict. And of course, you can't do that about the entire quantum state, even locally, much less globally, but you have to be able to grab some gross features of the system, sort of stuff I'm seeing looking out of the window, the trees and so on, very, very far from a complete description, and remember what they look like and do some predictions about how they will behave. And he says, well, computations can't work if there's too much background noise. Everybody who's tried to do any operate an old-fashioned computer where they had trouble with noise knows that even digital computers make a lot of mistakes. If there's too much noise, certainly analog computers make mistakes. You can't get a computer to work if it's swamped with noise. And Mallah points out that everything we're interested in, say, size of our brain and bigger, is in a very high dimensional Hilbert space, where every lump in phase space, a lump representing a macroscopic outcome, every lump in phase space is really mostly near its boundaries, because in high dimensions, surface to volume gets very big. Everything, you can't get anything that's in the middle of the lump for every single parameter. So everything in one way or another is near the boundary. And then he says, and this is the key step, where you have a condition on the state, not just an unconditional argument about a proof. What if there's some sort of background noise? Still just quantum state. It's not some other classical ingredient, but just sort of a background hum, kind of white noise in the quantum state. What would that do to our ability to compute or to be computers ourselves? Well, the only way you can beat local white noise is by doing a little signal averaging over some volume. Let me just try and picture what's going on here. This is an old-fashioned TV. Those of you who never saw CRT TV won't recognize this, some of you will, where you just got a bunch of background noise and you're trying to see things. Well, if you have an intense thing, you can see pretty small versions of it. If you have a less intense thing, you can see it, but you can't see the little versions of it. You need to do more coarse graining than you do out here in order to be able to see this less intense version. So the amount of coarse graining you have to do to see something depends on how intense it is. Or as you might say, it depends on psi.
Michael, just letting you know, 15 minutes left.
15 minutes, we're great, we're good. In fact, there'll be tons of time for arguments, questions, everything. So here's what Mallah says. Computations become hard to implement for a wave at or below some scale, acronym state crowding amplitude level scale. The crowded states are that background where there's a little bit of this and a little bit of that with random phase for all sort of different possibilities. So he says counterfactuals get ruined because states can be affected by incoming waves. Classical behavior does not emerge because decoherence cannot set in, and so on. Now, I like to think of it a slightly different way, just because it's simpler. The words are simpler. Let's ignore the lump in phase space, us and the tree and all the stuff we're looking at, and just think about the noise. The noise is in thermal equilibrium. It's at maximum entropy. But as Sean Carroll described last week, that's a time reversible situation. In a time reversible situation, there's as much recoherence going on as decoherence. And recoherence means the merging of macroscopically distinct pasts. Live cat and dead cat start interfering. Why? Because there's so many slightly different versions of them in this fully occupied state space that you can find a version or versions that match up in all these weird little details of their environment will find themselves and create a merged cat who had two pasts, one live and one dead. So we can't have anything like memory in a time reversible situation. It's the same argument that Sean Carroll made. And that means that these noise dominated regions cannot support computations. And that means thoughts being a type of computation, they can't support observations. So let's ask how many computations, if there is this sort of background noise? Well, signal to noise, just classical, how I made a living for many years, goes as the square root of the number of terms you've averaged. How many fine-grained states do you have to average over to get a signal to noise bigger than 1 if locally it's less than 1? Well, you have to average over a number of fine-grained ingredients that's proportional to, inversely proportional to the square of the local signal to noise, which means you get a number of independent coarse grain averages that's proportional to the square of the local signal to noise, or to slightly change the language, the number of outcomes is proportional to psi squared, which is a very nice result to get in unitary quantum mechanics without adding a collapse or Bohmian dots or anything like that. And so we are born again. Little just philosophical remarks. This will leave plenty of time for people to explain why they don't believe a word of this. I've talked about it as if we're viewing a coarse-grained screen. Of course, we're not outside the system viewing it. We are the coarse-grained screens ourselves. And you might object, well, there's sort of an anthropic selection left here. You're saying, we'll only get the Born probabilities and a probability rule that makes sense if there's this sort of white noise background. Aren't we then kind of doing an anthropic selection to say, there must be that white noise background in the world? Well, sort of, but it's actually a very mild anthropic selection. It's saying, yeah, the state has to, in order to be experienced and make sense, we have to have the right type of state. But we didn't know what type of state we were going to have anyway, so that's not so bad. What the other arguments are doing is essentially an anthropic selection on theories, saying any theory that doesn't insist on the Born rule being exactly right is incomprehensible. And even though it looks like the quantum theory we have would not give the Born rule under prima facie. So I'm arguing that the selection needed is actually weaker than the typical anthropic selection we already need. Again, as Sean Carroll pointed out, where the hell does this low entropy world that we live in come from? There's no good physical reason that we know of yet. There may ultimately be one, but it seems much more natural, Pache Tim, who doesn't like the word natural, to have a high entropy state. Most states are what you'd call high entropy. And yet somehow, by some miracle, we're in a low entropy state. It's not all that hard to say, well, maybe there's a little bit of high entropy stuff around too, which is actually much more natural, obvious thing for there to be than we are. So we're not requiring, we just require the existence for a coherent low entropy state, but we already require that, and we don't add to that a requirement of the non-existence of a high entropy background. We just say, yeah, maybe there's some high entropy background too. And in fact, we need it to get the Born probabilities. So that is actually it. That's the argument. I'll leave you with some links to the people who have published this argument. Patrick Van Esch's version, you know, some of us thought of that independently, but Jacques Mallah really came up with this wonderful idea, and he's only published it on the archive, but all I'm trying to say is people should pay attention to it, because I think it's where it's the best of many not very good stories as to where the Born probabilities come from. And that's it.
Questions?
So that, I mean, it went by a bit fast for me. Maybe this would help. I mean, there's talk about computations and that only in certain situations can something compute.
Yeah.
And you could say, look, there are observations that aren't in the normal sense of computation, right? Galileo drops a cannonball and a musket ball and says they land within 3 finger breadths of each other, and you
Sure,
say,
yeah.
in the obvious sense, it's not. But then you say, gee, but you need memory, blah, blah, blah. Okay, there's a bunch of stuff you need for a system to have to do what we'd call observing.
Well, I mean, just to be a little clear, there's
Yeah.
a bunch of stuff you need to be yourself,
Yes,
and you are
yes.
part of the system. Yeah.
And it looks to me like everything you said goes through just for plain old thermal entropy, right? If we're in thermodynamic equilibrium, there ain't going to be any observers. Okay, there won't
Yes,
be.
absolutely, absolutely. For thermodynamic equilibrium, no observers. Right.
So, but if I just replace thermodynamic entropy in this argument, I mean, I'm not sure what I'm supposed to get out of it. I mean, what does it tell me about probabilities? That the fact that I can't observe if the thermodynamic entropy is in equilibrium, sure. But what is I'm sorry, I just don't see the connection.
What it tells you is that
conceptual connection.
Ordinary classical signal to noise considerations give you that the probabilities that would emerge from this, that is the relative numbers of different versions of you observing different outcomes, would go as psi squared. It wouldn't go as something else. It would go as psi squared. And that is a good thing to have emerge from a theory, because it is what we observe.
I mean, all right, maybe I can try it this way.
Okay.
We know that in many worlds, there'll be worlds where you don't see Born statistics, for sure.
Sure, there'll be everything, but
and there'll be everything. There'll be worlds with observers that observe everything.
Yes.
Signal to noise won't get rid of them. So I just can't quite see how that signal to noise.
The argument is that the vast majority of worlds, of experiences, will look like the Born probabilities.
What's the measure by which you just measured vast majority? That's what I'm not understanding. You're not counting worlds.
We're sort of counting worlds. We're counting pieces of the density matrix that could represent a computation, that have reasonably good signal to noise, and therefore could be experienced as a thought, as opposed to just being a fuzz. And so it's, if the off-diagonal terms went to 0 more cleanly, then we could count worlds. But they're fuzzy. So we have to count good enough worlds. Let me go back and just ask you, is the problem with the toy model clear enough? The problem with, it looks like there are probabilities there. Van Esch has shown that those are consistent probabilities. They're just crazy. And they don't correspond to our experience. That would be world counting if the worlds were a little cleaner and more countable, like in our toy model.
That's clear. I don't see how that part is clear, but
Okay.
Saying there are fuzzy edges because of noise.
No,
I don't see how that affects the problem in I don't see how that affects the problem of counting measure when you're basically counting decoherent lumps.
We're only counting lumps that have been coarse-grained enough to have decent signal to noise. If there's a lump, but it's constantly got input from off-diagonal terms, remember time reversibility, popping up onto the diagonal the same way in the part of the state we usually think about, a diagonal term keeps drifting out, losing off diagonals. The time reversed is that very small off diagonals show up as a whole bunch of quantum interference terms between things that you thought were separate before. That would mean that those little separate things could not represent memories. Remember, think of how hard it is to predict quantum future. What if it was equally hard to remember the quantum past, which is what it would be if you were in a noise-dominated regime where time reversibility would apply.
Okay, then, well, I think that we run out of time for this quick Q&A session. So let's thank the speaker again. And let's reconvene here in 5 minutes.